Hi guys. Okay, so it is time for our next video. Hang on, I'm trying to get my stuff together here. Shouldn't turn my video on yet. Okay. Our next video, which is over chapter 18, where we're still in the chemistry half of physical science. So more on chemistry. This chapter in particular is about bonding and compounds, hence the title. And we're going to talk about the reason that compounds actually form. Like why does sodium bond to chlorine, or those kinds of things. And what the electrons are doing is like the most important thing to focus on. And so we'll go through some of that. We'll again label things on our periodic table, and you guys will continue to need to know element names and symbols and all that kind of stuff. So here we go. So atoms bond together typically because it makes them more stable. They like to have a certain number of electrons, which again we'll get to in a minute, and that arrangement of electrons when they share, when they are together, makes them more stable or changes their reactivity. It also, depending on the ways that the bonds are formed, can make a huge difference in the substance itself. And so just like we mentioned how, like salt, again, sodium chloride, you have Na, the sodium, which by itself is very reactive, can't be around water, can't be around oxygen, is poisonous basically to us. Combining with chlorine, which is a kind of a greenish gas, which is also poisonous to us in certain amounts. When you put those two together, they make salt, and we like to eat it. And so when you put elements or atoms together, even if they're the same atoms, if you arrange them differently, you can get two very different substances. So your book uses the example of graphite and diamond, which I think is awesome. Both of those are made of carbon. Remember, carbon is just plain old C on the periodic table. And depending on how they're arranged, you either get something like graphite, which is very inexpensive, it's black, it's soft, it's slippery, it's basically what your pencil lead is. Or if it's arranged just a little bit differently, you get a diamond. Very valuable, transparent, you can see through it, light shines through it, very hard, the hardest natural substance that we know of. And then I have a question mark down there where I'm comparing it kind of to the slippery because I didn't know it was the best way to compare it to being slippery. But both of those are made of pure carbon, or can be made of pure carbon. So they are different because of the way that the chemical bonds are formed. In graphite, which is this top picture up here, you have like hexagon shapes, these 6-member rings, and where each corner is, or where each, two lines meet, that's where a carbon is. And so those are the lines are showing the bonds. And so you have these hexagon shapes, and they bond together to form sheets, and the sheets are kind of weakly bonded together. Basically, when you are writing with your pencil, you are laying down like a sheet of carbon. That's what that graphite is. As you're kind of going along, and it wears down your pencil lead. So anyway. That's graphite, but then diamond, if you see it down there at the bottom of the page, so here's the diamond, it has a very much more three-dimensional shape, of course. You have these pyramids that are formed and make this really, really strong 3D network, and it completely changes the physical properties of that compound. So bonds. Super big deal, and as in the characteristics of compounds, and how they react and look and do all those different kinds of things. Okay, so now here's the deal with bonding. Bonding only involves the valence electrons, and what they are all trying to achieve, or what they're all trying to get to, is they're all trying to meet the octet rule. The octet rule says that elements bond so that their compounds have 8 electrons in their outer energy level, because this is the most stable form that they can get to. The only elements on the periodic table that are already there are the noble gases. That's why they don't bond with other stuff. They already have 8 electrons. Again, helium is an exception there, but for the most part, they have their 8 electrons, and so that's why they do not bond. Everything else bonds to get to that arrangement. Everybody else wants to be a noble gas, so they have to share or take somebody else's electrons. Okay, 2 ways that atoms bond. They either gain or lose electrons, and this is called an ionic bond, or they share electrons, and those are called covalent bonds. So the covalent, co always means sharing, so they're sharing their valence electrons. The bond type, whether it's going to be ionic or covalent, depends on how strongly an atom attracts electrons or how strongly it is holding on to its own electrons. Okay, so this whole process of, how attractive is an element or is an atom to its electrons, that is called electronegativity. Again, it's just a word, but know what it means. This is a periodic function. So remember we talked about metallic property being periodic function, atomic radius being a periodic function. As you go across the periodic table, these periodic functions change. And with electronegativity, the function or the trend that you see is that elements that have more valence electrons have a higher electronegativity. Those are the elements that are to the right side of the periodic table. And so these are, and when I'm talking about sides, remember that kind of zigzag line that we put on there. It's kind of the division. But the higher the electronegativity, let's see, I'm going to put the right side over here, so hopefully you'll remember that we're talking about the periodic table. And then the elements on the left side have a lower electronegativity. And that is something, by the way, that we will put on our periodic tables, or we'll kind of label both sides. Okay, so now the bond types. We've got covalent bonds. These typically are between elements that have similar electronegativities. That means that they both are equally attractive to the electrons, and so they can't really take from each other. So it's like an equal pull, like tug of war between two teams that have the same strength. And so instead of one taking and the other one gaining, one taking and the other one losing, they're similar, and so they end up having to share them. Ionic bonds are between elements that have different electronegativities. One is high and one is low, and so one has the ability to take electrons from the other. And then metallic bonds, these are typically between metals, you guessed it from the name, and the elements that are involved here, all of them have low electronegativities, and you see kind of a group sharing of electrons. Okay, so with covalent bonding, we've got elements with similar strong electronegativities, so no one can take electrons from the other, and they share. And so in this whole process of sharing, all of the atoms involved have 8 electrons. There are some exceptions to that. Hydrogen is an exception because it can only have 2 electrons, but in general, 8 electrons is what everything's going for. And so covalent bonds is just the sharing of one or more pairs of electrons between 2 atoms. So typically when you are illustrating covalent bonds, you use a Lewis dot structure. We did this in chapter 17 where you guys did the dots around the symbols of the elements. We're going to do that same thing, but now we're going to put them together to show that sharing between 2 different atoms. So if we have a chlorine molecule, Cl2, it means I've got 2 chlorines bonded together. When you draw them out, you're going to draw each one with its electrons. And so this is what we wrote on our periodic tables. If you look on your periodic table, chlorine is in group 17, and so it is going to have 7 dots around it. So I'm going to draw one chlorine to start with. So here's our first chlorine with its 7 electrons to start with. Now, the second chlorine, I'm going to do it in a different color just so it is, you can see, let's see, green. So you can kind of see the difference. So now you kind of make them fit. So if the second chlorine also has 7, if I put it over here and I give start electron here, and I got here, now this next section, so this little part over here, that's where they're sharing. They don't need any more electrons there, but I've still got to finish up the other electrons that chlorine had originally. And so now you have both atoms having having 8 electrons around them. Let me see. Draw a circle around each one. So this chlorine is next to or close to 8 electrons, and this chlorine is also has its 8 electrons, and so they are sharing, where I have that arrow, they are sharing those 2 electrons. That is a shared pair, and that is what is holding them together. Now, with covalent bonds, you can have a single bond, which is what we just drew on the previous page. They share, each atom contributes 1 electron, and so they have that pair, the 2 between them. In double bonds, they each share 2, which means they're actually sharing 4, so you have 4 electrons that are being shared. Triple bond, they each share 3, so they have 6 total electrons that are between them. Excuse me. Okay, so Lewis-Stokes structures for this. So here's our chlorine again. I'm not going to do the first one since we did this. But then oxygen. When oxygen is bonded to itself, you have an oxygen molecule. It tends to form a double bond. That's not tends, that's what it does. And so what you end up having, so here is oxygen. Remember, it's going to look like this with 6 electrons to start with. So there's that. So those 2 single electrons that you see there, those are the ones that are going to end up being shared. So when you put them together, everything kind of shifts a little bit, and so those 2 end up on the same side. Then the other 2 kind of get moved, and then the other oxygen is kind of going to look similar. It's going to have 2 here, and then 2 kind of over to the sides. So again, if I put circles around them, that one has 8 electrons around it, and this one has 8 electrons around it. This a lot of times is written like this, where it'll look like oxygen with just like an equal sign between it to show that double bond. Nitrogen as a molecule will share 6 electrons between it, and I'll just show you like the simple form. It would look like this, nitrogen with 3 around it. And these both actually have 2 other electrons on either side, so they still have their 8 electrons. And this oxygen would still have these other 2 electrons up there. And we're not going to do really crazy stuff. Oh no, we're not going to do really crazy stuff with our drawings, but I did want you to kind of see kind of those little more advanced ones. Okay, polyatomic molecule. So it doesn't just have to be 2 elements that are the same, that are bonded together. Water is considered a polyatomic molecule. The prefix poly up here, that means many. So many atom molecules basically means more than 2 or more different elements. So water, of course, you guys know, is chemical formula H2O. So when it forms, you have something that looks like this. So here's our oxygen with its 6 electrons. There's one more there. Okay, and then when it bonds, each hydrogen has 1 electron. So one's going to bond here, and 1 is going to bond there. And so that is the structure for that. Ammonia, it is actually called NH3, or it's written as NH3, and it will again do the same thing. Nitrogen has 5 electrons around it. Kind of written big here. I'll try to finish this one in here. NH3. So there's the N with its 5 electrons, and then each hydrogen, you have 3 of them, just fills in where it would be missing right there. And so that one looks like that. Methanol is a little bit more complex. Its formula is actually ch3OH. So it looks like that. Typically, the carbon is going to be in the middle because it can form the most bonds. And again, this is kind of a complex one. We wouldn't really do this one. But it would end up with 8 hydrogens on 3 of these sides. And then we throw in this oxygen, and it's going to have 1 bond between it and the carbon, and then it's got this other one with that last hydrogen right here. So anyway, so it's kind of like a puzzle where you kind of fit everything together. And so we'll do really simple ones in class, but just kind of know they can get pretty complex if you get into the bigger molecules. Okay, so now with these covalent bonds, you also typically see what they call a polarity, or you can kind of determine polarity. And here's the deal with this. In covalent bonds, the electrons are shared, but they aren't always shared equally. And so sometimes you have kind of different types of bonds. If you're talking about diatomic elements, remember we wrote down the 7 diatomic elements on our periodic table. We call those the Brinkelhoffs. Remember those? If you have 2 identical elements bonded together, then they have identical electronegativities. They have an equal or identical attractiveness to electrons. So that means there's no difference in their electronegativity number. So that's what this the delta En equals 0. So nobody is stronger than anybody else. So you have equal sharing, and this is typically called a non-polar bond. So no polarity, equal sharing. But what if you have 2 different elements and they have different electronegativities? For example, hydrogen and oxygen. So that makes up water, H2O. Oxygen has a higher electronegativity value, and there are numbers that go along with the electronegativity value. Don't worry about the actual numbers. I'll tell you which one's higher or lower. Oxygen has a higher electronegativity value than hydrogen, and this means that the electrons that they share are actually going to be more attracted to oxygen and are going to be closer to oxygen. And this is an unequal sharing, and this is what we call a polar covalent bond, or this unequal sharing. This is the thing, like, if you're sharing like a pack of M&Ms with your, much younger sibling, and you're like, 2 for me, 1 for you, 2 for me, 1, they're sharing still, but somebody is getting a little bit more. And the same thing happens with atoms and the electrons that they are sharing. Gives them a different shape, gives them one area that's more negative and one area that is more positive, and it just makes them chemically a little bit different than if it were equal sharing. Okay, so with this polar covalent bond, I may have kind of already said all of this, you end up with one atom that has more of the electrons. If it has more electrons, that means it has a negative charge. Electrons have a negative charge. And then you have one atom that has a positive charge because it has fewer electrons closer to it. So you have a positive and a negative region. And that's where we get the word polar. It's like the North Pole or the South Pole. You have this positive, negative, like a magnet. Polar covalent compounds are very good at holding themselves together because the polar end of one molecule will attract the negative end of another, and then those molecules will be closer together. And this is called an intermolecular force. Holds together things like ice and sugar, water. So like here's our water. So if we drew water, you usually see it drawn something like this, with an O and 2 H's attached to it. Now, in water, there's a line basically that divides them. This is the negative region, and this over here is the positive region. And so when you have a whole bunch of water, so if I've got H2O, and then I've got H2O, 2O, and I got another H, oops, 2O over here. This oxygen, because it is negative, tends to be attracted to the positive half of this other water molecule, so they bond, and then this hydrogen is attached to this oxygen, and so they bond, and so it goes on from there. But you have this intermolecular force, and that is why water, for example, has the properties that it has. Okay, so now with the covalent bonding, you can determine the number of bonds that can form, the number of electrons, and this all goes back to the shape, or it helps determine the shape, and it has a big influence on how these different molecules will react. And so again, this is just kind of practice drawing them. So if you have CH4, the way that you know how to draw these, typically the element that has more valence electrons is drawn first, so it's kind of in the middle. So carbon is in group 14, and so it has 4 electrons around it. So here's our carbon. And then each hydrogen has 1, and so there's 4 of them, and so they bond. I know my dots don't look great, but so they bond like this. This is what they would call a tetrahedral shape. And so it's very symmetrical, very equal, everything is kind of spread out nicely. To me, that doesn't really mean a lot, but it does determine chemically how that element will react, or how that compound will react. Okay, so CO2 is carbon dioxide, which you are currently exhaling. Carbon, again, has 4 electrons around it in this case, and I won't typically have you do, but carbon and oxygen actually tend to form double bonds. And so I'm going to draw it like this, just so you guys can kind of see it. So here's the oxygen with its 2 electrons on either side, and then it's going to have its other, for the 6 that it has, oops, 6, 6, so it's going to look like that. And this one has more of a linear shape, which again is kind of helps it react the way that it's going to react and do the things that it is going to do. Water, the O is what we kind of start with, because it's got the most, valence electrons, and then each H would go on these sides, and it has kind of a they call it an angular shape or a bent shape. And again, all of those different shapes, we'll do more with that when you guys are in chemistry in a couple of years, but those shapes determine how they function with other chemicals and in chemical reactions. Okay, so with these covalent compounds, some kind of general characteristics. They are formed by the joining of different molecules. Most often in covalent compounds, it is the joining of 2 nonmetals. They're not very strongly bonded together. They can be solids, liquids, or gases. They're very random group. They have low melting points typically. They tend to be very strong physically, but lightweight and flexible. And then they don't dissolve easily in water, which sounds like these two are kind of contradicting each other. They're not strongly bonded together, but they are don't dissolve easily in water. When I say not strongly bonded together, that's basically the intermolecular force. So as a compound, they don't hold themselves together super well. Oh, I'm totally butchering that word there. But as a molecule, they do not dissolve very easily in water. And that's really good for us because we are mostly composed of covalent compounds. So we wouldn't want to have our cells dissolve really easily in water, because that would kind of defeat the purpose of, being alive essentially, because we wouldn't be. And so they're kind of random as far as reactions and stuff. Okay, now moving on, ionic bonds. These are when one electron or excuse me, one atom takes electrons from the other atom. So you have transfer of electrons. So elements that have higher electronegativities take electrons from the elements with lower electronegativities. And once the electrons are taken, the atom that takes has a very strong negative charge because it has more electrons. The atom that has lost has a positive charge because it has lost those negative charges. And then you have a positive negative, and that's what actually holds them together. They are attracted because opposites attract. Positive is attracted to negative. Okay, so now when you draw these, they're drawn a little bit differently as far as what is happening, and so it's kind of a little more involved. But you have, so if we have sodium and fluorine, Na and F. So here is Na, and it has one valence electron. It's in column 1, and then we have fluorine. Fluorine is over there in column 17, so it has 7 valence electrons that look like this. Okay, so now remember that the one that already has a bunch of valence electrons is going to have the higher electronegativity. So fluorine is much more attractive to electrons than poor old sodium. So that one little electron that sodium has is going to see fluorine over there, and they're like, wow, you're really attractive. So this one little electron will go and join or go and be part of fluorine's outer energy level. So now you have this. You have sodium, sad little sodium. It has no valence electron, so it has lost its one negative. So if you do the math, if you do minus a -1, because electrons have a negative charge, that gives you a +1. And sodium now ends up, and they write them in brackets just to show the ions or the charged particles, it has a +1 charge. That's sodium, but then right next to it, here's fluorine, has its 7 original electrons, has that 1 from fluorine, excuse me, and it also is written in a bracket, but now it has gained a negative charge. So now it's like us saying plus -1, and that's a -1. So now we have a +1 and a -1, and that's how those two are joined together, because the positive and the negative are attracted to each other. The way that you make sure that these are written correctly is as if those numbers equal 0. So +1 and -1 equals 0. And I know this is kind of tedious, and we won't do a ton of it, but it is what is happening with the electrons. It's why certain things join together. Okay, now let's see, magnesium and sulfur. So we've got magnesium. Here's magnesium. It's in column 2. So it has 2 valence electrons. And then we have sulfur. Sulfur is in group 16, so it has 6. So of these two, sulfur is more attractive to electrons because it has more to begin with. So these 2 electrons on magnesium are like, see ya. We're going over here to sulfur. So you have sad little magnesium now, no valence electrons. It's an ion. And if you have lost 2 electrons, minus -2, you get a +2. Okay? And then you have your sulfur. So sulfur's over here all happy with all of its electrons. 2 of them we'll draw in green because they are the 2 that came from magnesium. And those extra 2 electrons, -2, is the charge that they give us, and +2 and -2 give us 0. Okay, now the last one, there's a little extra step to it. Magnesium, we already said, is Mg, and it's got 2. And then we've got, let's see, we'll do our fluorine blue again. Fluorine has 7 already. Oh, stop doing that. 7 electrons. Okay, so now only one of these can go because that's the only space it has. But where one fluorine is, there will be another one. So there will always be enough of the other element to bond to, or to take that other electron. So when you draw this one, all these steps, you have Mg, oops, let me try and keep my color straight here just so, if that's helping you, not confuse you. Okay, so I've got Mg, and it is +2. And then I've got my 2 fluorine. So I've got F dot, 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 dot. 1 from fluorine. So that's a -1. And then I have another one. I have dot, 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 dot. If not all my dots are showing up, it's because my little camera thing is in the way. Extra dot. And then I've got my other, and that's -1 also. So +2 -1 -1 equals 0. Ooh. All right, so that is showing what is happening with the ionic bonds, where the electrons are going, where they came from, how they are transferring. Okay, so with ionic compounds, they are a little bit more structured internally sometimes. They can exist as what they call crystal lattices, which basically just means they have a very regular and repeating 3D pattern between the positive and the negative ions. So the one that lost electrons and the one that gained electrons. And these compounds are represented by what they call formula units. And these are basically like the reduced form of an element. And so, for example, even though even in a single grain of salt, you actually have 100 sodium ions and 100 chlorine ions. They're all stuck together. So you would want to write it, you know, well, like I have here, Na10Cl10, because those two numbers, like a fraction, because those two numbers you can divide them both by 10 and get 1. You simply write it as NaCl. So you always write in the most reduced form. So anyway, and then the big structure themselves, they're made up of these unit cells, which are just the repeating structure pieces. Okay, so with these ionic compounds, some properties. First off, they are made of elements that have different electronegativities, typically a metal and a nonmetal, or a metalloid, as I have on there. They are solids. Ionic compounds are, there's no other option. They're going to be solids. They're very brittle typically. They have a very distinctive crystalline shape. They tend to have high melting points, like, you know, like surface of the sun high. I mean, like throw them in a volcano high kind of a thing. But strangely, they do dissolve easily in water. And when they dissolve in water, they form electrolytes. And these are the things that help a solution containing an ionic compound. That's what helps them conduct electricity. And so, for example, salt dissolves very easily in water. Salt water is very good at conducting electricity. Okay, now last type of bond, metallic bonds. Metals typically follow what we call the free electron theory. And this is where all of the valence electrons in a metal are shared by all of the atoms. And this is like sharing on a much larger scale. It can be between 2 or 4 or even more atoms than that. And so you have these positive metal ions, and they are embedded in like a sea of negative electrons. And the electrons just kind of flow and circle around all of them and just kind of keep moving around and holding them together. And it's unusual because they don't necessarily meet the octet rule for each individual atom, but as a group at any one time, they are meeting that octet rule. And metals, of course, can be all just one type of element, like all aluminum atoms, or they can be alloys, which is where you have metallic bonding between different types of metals. Alloys tend to be stronger than pure metals. So like, and we talked about this a little bit already, I believe, but like, pure gold tends to be very soft, and you can kind of, change its shape, which is not very good for like jewelry if you want it to keep its shape. And so that's why you have different karat gold, and that just means different amounts of other metals that have been added in to strengthen them. Okay, so metals follow another kind of a lattice structure, and naturally they try and fit together to take up the smallest amount of space possible. They're trying to pack in as closely as they can be, and this has been determined to be what they call the hexagonal close packed arrangement. And so you have a hexagon, and so in that picture down here, you have the hexagon. So notice it has 6 sides to it, hexagon, and then in between it you typically have kind of something that fills in so they can fit together as closely as possible, like a little 3 atom structure. And these alloys, this packing is even easier with different types of metals, and this makes them very resistant to rusting, gives them extreme hardness compared to pure metals. And so it's again kind of a structure of how the elements are, or excuse me, how the atoms are fitting together. Okay, last page. So substances with metallic bonds. First off, they tend to conduct, electricity very well as solids, because the electrons are just free and available to carry that current. They also conduct heat very well. They're shiny. They have that luster. Even though they can be harder, depending on if they're alloys or not, or what they are, they do have a tendency to be malleable and ductile. So, there you go. So that's the different types of bonds, how they're formed, some of the visual structures that we'll draw. Of course, ask me questions if you have it, and I will see you guys in class. Bye.